This is my diagram of a refrigerator, and we're just going to go through the steps. And remember, everything in this blue box off to the left is inside your fridge, and everything else is kind of exposed to your kitchen. Okay, so in step one, we have our refrigerant, and it's a cool, low-pressure gas, and we put it through a compressor. And this is why you have to plug your refrigerator in. It takes energy, and it uses it to compress the gas, so it puts it under high pressure. But by doing work on the gas, it transfers energy to it. So not only is the gas under high pressure, it becomes very hot. So in step two here, we have a hot, high pressure gas that's moving through this tube. And because it's hotter than your kitchen, right, they'll start to equilibrate with your kitchen. So it's going to start dumping some heat out, which is good. Okay, so we're dumping heat out, and we're a high pressure gas. Now remember, because it's under high pressure, it's easier for that gas to become a liquid, right? It'll do it at higher temperatures. So as it starts dumping heat off, it actually becomes cool enough for the liquid to start to condense. And now, this is the really interesting part. These kind of black arrows with the Q's are representing the heat of vaporization. So remember, the heat of vaporization is that kind of energy we need in potential energy to go from a liquid to a gas or a gas to a liquid. And this is the plateau, remember, in a heating cooling curve. And it's a really long plateau, so it's a lot of energy. And as this gas goes from a gas to a liquid, it's going from zero potential energy to negative potential energy, right? And there's a big jump there. And so the liquid actually has a lot less energy than the gas does. Where does that energy go that it used to have? Well, it dumps it out as heat of vaporization, right? It kind of releases all this energy. And that's what these black arrows are with the Q's. There's all this extra energy that's being dumped out because the gas is condensing to a liquid, right? And it kind of has a big drop in potential energy. That's all that energy that it doesn't have anymore, right? It releases. And this is why steam burns are especially bad, right? If you have a hot gas and it condenses onto your hand, not only is it hot, which sucks, but when it condenses, it releases that heat of vaporization, which is a huge amount of energy, and that makes those burns especially bad. And so this liquid now gets all this extra energy that it releases, and so it's making your kitchen even warmer, right, as it equilibrates. But it gets to spend time to cool down, but also heat up your kitchen, which is why your refrigerator is actually warm in the back, right? That's all that energy that it's releasing. So we end up with this kind of warm, high pressure liquid, right, which is kind of started to try to come to equilibrium with your kitchen, still high pressure. Now in step four, it's allowed to go from a high pressure zone to a low pressure zone. And this is really important. So when we have that high pressure liquid and we let it go to the low pressure zone, remember, as the pressure drops, it's easier for the liquid to become a gas. So a lot of that liquid will vaporize immediately. And as it, goes from liquid to gas, the reverse happens as in step three. And this is, again, evaporative cooling. So all that energy that's involved in that potential energy, right? So we have liquid, which has a negative potential energy, and it's going to a gas, which has zero potential energy. So it's gaining all this extra energy in that potential energy. Where does that energy come from? It has to absorb it from its environment. And that's why these black arrows, are pointed inward now. Because as that liquid begins to vaporize, it has to pull energy in, right? And it makes everything else much colder because of that heat of vaporization. And so now your warm, high pressure liquid becomes a really cold, low pressure liquid and gas as some of that liquid vaporizes into gas. And now that it's colder than the inside of your fridge, it can start picking up energy from whatever's in your fridge, and it makes your fridge colder. And again, this works second law of thermodynamics wise because we're going from hot to cold. It just happens that the inside of your fridge is the hot part and the really cold tube is the cold part. And as it picks up all this extra energy, that liquid will eventually all vaporize into gas, and you're left with this cool, low pressure gas, which then goes to the compressor. And the cycle just rinses and repeats. Now I want to show you a little kind of graphical thing. It's not exactly kosher, but I think it helps to understand. So we start out with a gas, and this is a PT diagram. And we put that gas under high pressure, which also heated it up. So we go out here. Then we let it cool down where it became a liquid. And then we put it under a low pressure where it became a gas again and cooled down, and then was allowed to warm back up from the inside of your fridge. And this is kind of that cycle that it goes through. And remember, the heat of vaporization is key.